Welcome back to trigonometry. Today we're going to be looking at something called de Moivre's theorem. This theorem is going to be very helpful when looking at powers and roots of complex numbers. So here we go, de Moivre's theorem. And we're going to use it to look at powers and roots of complex numbers. Now in the previous lesson, previous podcasts, we looked at how to multiply complex numbers together. We learned that if you have two complex numbers in polar form, like if you have r sub 1 times cosine theta 1 plus I sine theta 1, and let's say you have r sub 2 times cosine theta 2 plus I sine theta 2. We learned that we could take those two and multiply them together. Multiply this complex number with this complex number, and we developed this little shortcut kind of formula that you can take r1 times r2, and then you could take cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. You know, we developed that, and once you develop a formula, you can use it from then on. We developed that in a previous lesson. Well, today we're going to take this a little further, and we're going to look at it and how it applies to finding powers. Let's say that your two complex numbers are identical. Let's say you have r cosine theta plus I sine theta, and let's say you're multiplying that with another r cosine theta plus I sine theta. So essentially what you're doing is finding r times cosine theta plus I sine theta squared. But you can also apply this little rule here. You can say, well, that's the same thing as r times r, and then cosine of theta plus theta plus I sine of theta plus theta. So you get r squared times cosine 2 theta plus I sine 2 theta. Which is kind of an interesting result. You square it, and you get r squared times cosine 2 theta plus I sine 2 theta. Okay then, what if we're cubing it? What if we take r times cosine theta plus I sine theta, and what if we cube it? Or we can take r times cosine theta plus I sine theta, which is already being squared. We know what that's going to come out to, and we can multiply that with r times cosine theta plus I sine theta. Well, we already know the squaring gives us r squared times cosine 2 theta plus I sine 2 theta. And if we're multiplying that with r times cosine theta plus I sine theta, then we're going to have the r squared times r, which is going to give us r cubed. And we're going to have cosine of 2 theta plus theta, which is 3 theta, plus I sine of 2 theta plus theta, which is 3 theta. So there seems to be a pattern here. And you can go on and continue, and you can prove that this pattern does keep going, so that in generic terms, you can take r cosine theta plus I sine theta raised to the nth power and get r to the n times cosine of n theta plus I sine n theta. So you get that. And this is stated for n is any real number and r times cosine theta plus I sine theta is a complex number. So n is any real number, which means it can be positive, negative, it can be fractions. We're going to stick with looking at positive integer values on some, and then we're also going to look at like positive fractional values, but it can be applied to any real number, which is very handy. Let's say you have a question like this. Let's say you have square root of 2 plus I square roots of 2, and we want to raise it to the 5th power. Well, you could multiply 5 of those together. 5 of those together. Instead, let's use the Moivre's theorem. So let's first put this into polar form. Okay, so let's see here. We've got square root of 2, square root of 2. Yeah, real versus I. Alright. If that's the case, if that's square root of 2 and that's square root of 2, r is going to be square root of 2 plus 2, which is 2. The theta in this case is 45 degrees. Alright, so square root of 2 plus I square roots of 2 equals 2 times cosine of 45 degrees plus I sine of 45 degrees. Alright. Now let's say we want to raise both of those to the 5th power. Well, that's where we can use de Moivre's theorem. We can take this 2, raise it to the 5th, and then take cosine of 5 times 45 degrees plus I sine of 5 times 45 degrees. So we get 32 times cosine of 225 degrees plus I sine of 225. Okay, so this is in polar form. Let's put it back into rectangular. We've got 32 times, well, the cosine of 225 degrees is negative square root of 2 over 2. And then the sine of 225 degrees is also negative square root of 2 over 2. So you do a little simplifying, you get negative 16 square roots of 2, and then minus 16I square roots of 2. And there it is. You're able to use de Moivre's theorem to pretty quickly take that complex number and raise it to the 5th power. I think it's faster than actually taking square root of 2 plus I square root of 2 times itself 5 times. De Moivre's theorem makes it a lot faster. Okay, So there's that. Now, again, too, I did mention that this theorem, the n can be any real number. So what if you're dealing with a fractional n? All right, let's say you've got a complex number and you want, and this is raised to 1 over the end. 1 over the end, essentially you're finding roots. Finding all complex roots. Well, we can tweak the Moivre's theorem a little bit. That's going to equal r to the 1 over n times cosine of n theta over n theta. Let me erase that. I didn't write it in a very good spot. Try that again. Cosine of 1 over n theta plus I sine of 1 over n theta. Or you could say nth root of r times cosine of theta over n plus I sine of theta over n. Okay, so you can do that, but this will only find one root. Apply to theta plus 360 degrees, or theta plus 2 pi, depending on which one you're dealing with. And let's say 360 degrees times k, or 2 pi times k. So let's look at not just the theta, but let's look at all coterminal angles. You know, if you go around 360, coterminal angle. If you go around 2 pi, the coterminal angle. So let's apply it to that. So let's make it a little more generic so that we can actually find all of our roots. So we're going to do nth root of r times cosine of, you could say theta plus 360 degrees k over n plus I sine of theta plus 360 degrees k over n. Or you can do nth root of r times, if you're doing it in radians, cosine of theta plus 2 pi k over n plus I sine of theta plus 2 pi k over n. So this will take care of all your coterminal angle cases. And you've got, you know, whether it's in degrees or radians, so you got both options. And by the way, you know, n could be any real number, but typically here we're going to be dealing with positive integers. But k is going to be a whole number, 0, 1, 2, 3, etc., all the way to n minus 1. Like if you're finding the cube root, you're going to take k from 0 to 1 to 2. And you'll stop before you get to 3. If you're finding the sixth root, you'll take k from 0 to 1 to 2 to 3 to 4 to 5. And you'll stop before you get to 6. Because the sixth root, there's 6 roots. Cube root, there's 3 cube roots. So if you do k as 0, 1, and 2 for a cube root, that takes care of all 3 of the roots. Alright. Now what's really cool too is once you find all your roots, if you go ahead and graph them on like a real versus imaginary axis, you will see all the roots fall on a circle equally spaced apart. We have a problem later we're going to do, and you'll see it. It's pretty neat. Alright, let's say we need to find all cube roots of, find all 3 cube roots of negative 8. So negative 8, if you graph it, it's going to be over here somewhere. So negative 8 is the same thing as negative 8 plus 0i. In this case, the r is 8, and theta is 180 degrees. So let's go ahead and write, this is in rectangular form, negative 8 plus 0i. Let's go ahead and write it in polar form. So go ahead and write 8 times cosine of 180 degrees plus I sine of 180 degrees. Alright, and if we want to find the cube roots of negative 8, then we're going to have to do the cube root of the r, the 8, times cosine of 180 degrees plus 360 degrees k over 3, because we're doing cube roots, or index is 3, plus I sine of 180 degrees plus 360 degrees k over 3. Okay, and since we're doing cube roots, we're going to deal with k as 0, 1, and 2. And we're going to find each situation. Alright, so for k equals 0, yeah, cube root of 8 is 2. Then you got cosine of, k is 0, so just be 180 over 3, so cosine is 60 degrees plus I sine of 60 degrees. Okay, so if you work that out a little bit, you're going to get 2 times 1/2 plus I times square root of 3 over 2. So you're going to get 1 plus I square roots of 3. That is actually one of the cube roots of negative 8. If k is 1, you're going to have 2 times cosine of, well, 180 plus 360 is 540, and then divided by 3 is 180. So you're going to have 2 times, and then you got negative 1 plus I times 0. So you're going to get negative 2. If k is 2, you're going to get 2 times cosine of, well, 360 twice is 720, plus 180, you're going to get 900, divided by 3, you're going to get 300. Okay, so that's 1/2, cosine of 300 is 1/2, plus I times sine of 300 is negative square root of 3 over 2. So we're going to get 1 minus I square roots of 3. And there you go. If you tried to go further, if you tried k equals 3, well, 180 plus 360 times 3 over 3, let's see, 360 times 3 is 1080, plus 180 would give you 1260 over 3, which is 420. But that's coterminal with 60. So you're going to end up right back to here. And then if you try to do k as 4, you'd end up right back to 180. If you try to do k as 5, you'd end up back to 300. And it just would keep repeating. All remaining angles, if you kept going, those angles would all be coterminal with these 3. So you can stop here. So you have found all 3 cubed roots of negative 8. If you took 1 plus I square roots of 3 and cubed it, you'd get negative 8. If you took negative 2 and cubed it, you'd get negative 8. If you took 1 minus I square roots of 3 and cubed it, you'd get negative 8. So you guys probably knew already about the negative 2. It's like in intermediate algebra and college algebra, like find the real roots. Well, the real cube root of negative 8 is negative 2. But if you're finding cube roots, there's actually 3 cube roots. Just the other 2 here are complex numbers, non-real complex numbers. The 1 plus I squared roots of 3 and the 1 minus I squared roots of 3. And the really cool thing is if you graph these, you're going to find that they all fall spaced equally apart on a circle. Like if negative 2 is here, you've got 1 plus I square roots of 3 and 1 minus I square roots of 3 and negative 2. They're all equally spaced out on a circle. And that's going to be true for any time you find all the roots of a number. The roots would all be equally spaced out on a circle. Alright, let's do another one. Let's see here. Let's do one where we're solving an equation. Right here. Let's say you have something like x to the 6th plus I equals 0. And you're trying to find all values of x that'll make this work. We'll subtract I, x to the 6th equals negative I. So to find x, you're trying to find all the 6 roots of negative I. Trying to find all the 6 roots. Well, let's see here. Negative I, just quickly roughly sketching, might be about right here on your graph. So that's 0 minus I. R is 1. Theta is 270 degrees. Okay, so negative I is the same thing as cosine of 270 degrees plus I sine of 270 degrees. But we are trying to find the 6th root. Okay, so according to de Moivre's theorem, what we're going to do, you basically have the 6th root of 1 for this, because R was 1 out here, times cosine of 270 degrees plus 360 degrees k all over 6 plus I sine of 270 degrees plus 360 degrees k all over 6. The 6th root of 1 is 1. Okay, so if k is 0, you're going to have the cosine of, 270 divided by 6. 6 times 4 is 24. 6 times 5 is 30. So cosine of 45 plus I sine of 45. Now if k is 1, basically you're taking the 270 over 6 is 45. And if k is 1, you got 360 over 6, which is 60. So essentially you're just adding 60 degrees. Oops. So if you look at this right here, that's really 45 degrees plus 60 degrees k. And so is this. So just keep adding 60 degrees. If k is 2, you're going to have cosine of 165 degrees plus I sine of 165 degrees. If k is 3, you're going to have cosine of 225 plus I sine of 225. If k is 4, you're going to have cosine of 285 plus I sine of 285. And if k is 5, you're going to have cosine of 345 plus I sine of 345. And if you try to go further, if you did k is 6, you get 405 degrees, which is coterminal with 45. So you just stop there. So there's all your roots in polar form. The really cool thing about that is that they're going to be equally spaced out on a unit circle. Like if this is 1, if this is negative 1, if this is 1, and this is negative 1. Okay. Cosine of 45 plus I sine 45. If you draw the vector, you're going to, let's see, I'm using a protractor here. So if you draw a vector, that particular one's going to end up going to here. Okay. That was for cosine of 45 plus I sine 45. All right. Now for the next one, for 105. 105 is right here. If you're drawing a vector, goes right there. So there's your cosine of 105. Plus I sine of 105. And for the next one, let's see, for 165. Going to here. If you're drawing the vector. Go to there. So that's the cosine of 165 plus I sine of 165. 3 down, 3 to go. Okay, and if you're doing 225, next one was 225. So 45 right here. So if you're doing the vector, start here at the origin and draw it. Okay, so that's your cosine of 225 plus I sine of 225. And then your next one, you're looking at 285. So draw your vector. Here. There you go. And then finally for 345. To here. So draw your vector. I'm not perfect at drawing this stuff, but you get the idea. Okay. As soon as you try to add 60 more degrees and go to 405, you're going to be back here at this vector. So just after that, every other angle is coterminal. But there you have it. That's all complex number solutions of x to the 6 plus I equals 0. And we graphed each solution as vectors in the complex plane. So and they all, we went ahead and graphed them all on the unit circle. Notice they're equally spaced apart, all 6 of them. And there you go. Okay, so that's de Moivre's theorem, being able to use it to find roots of complex numbers. And so, you know, any real numbers can also be, you can also use de Moivre's theorem because a real number is a complex number, just the real part and no imaginary part. So we did that earlier with -8, but then we also demonstrated we can do it with a complex number like -I. You can do it with any complex number. You can do it with 3 plus 6i or something. You know, just follow the same procedure of put it into polar form, and then apply de Moivre's theorem to finding all the complex roots. If you are trying to find the cube root, you're going to find 3 cube roots. You're going to use k equals 0, 1, 2. If you're trying to find the 5th roots, you're going to find 5 of them. You're going to use k as 0, 1, 2, 3, 4. You know, and they're all going to be equally spaced apart if you graph them, and they're all going to fall on a circle. Pretty cool stuff, huh? Alright, well that's not the end of polar stuff. We do have to talk about graphing polar equations, like talk about polar equations and graphing them. So do tune in again, because the polar journey continues. And I think it'll be lots of fun. Maybe not as fun as the Polar Express, but hey, it'll be fun in the math kind of way. Well, thank you for joining us.